Without any waste of time, now let me introduce you to our first speaker of the day, which is Mr. Gilad Shainer from Nvidia, the company that develops the GPU accelerators. Mr. Gilad Shainer serves as Senior Vice President of Networking at Nvidia, focusing on high-performance computing, artificial intelligence, and the InfiniBand technology. Mr. Shainer joined Mellanox in 2001 as a design engineer and later served in senior marketing management roles since 2005 at Mellanox and now Nvidia. Mr. Shainer is the chairperson of the HPC AI Advisory Council organization and the president of UCF and CCIX consortiums, a member of IBTA and a contributor to the PCI-SIG, PCI-X, and PCIe specification. Mr. Shainer holds multiple patents in the field of high-speed networking. He's a recipient of 2015 R&D 100 Award for his contribution to the core direct in network computing technology and the 2019 R&D 100 Award for his contribution to the Unified Communication X, UCX technology. Gilad holds an MSc degree and a BSc degree in electrical engineering from the Technion Institute of Technology in Israel. He's accompanied by Mr. David Slama. David Slama serves as Senior Director of Marketing for Networking at Nvidia, focusing on high-performance computing, artificial intelligence, cloud-native supercomputing, and the InfiniBand technology. Slama joined Mellanox in 2005 as a SW engineer and served in several SW management roles until 2020 at Mellanox. He led cloud solutions, Ethernet and InfiniBand SW management, storage, automation solution, and upstream activities such as Ansible, Kubernetes, OpenStack, Puppet, Chair, and more. Slama holds a patent in the field of ML, machine learning, and AI, artificial intelligence for networking. He has an MA in government and a BA in management and computer science. Welcome to the Hpc National Conference, our colleagues from Nvidia. Now, I was told that Mr. Gilad is not available to present and interact with us. However, he has sent us the presentation, which will be played now. Afterwards, Mr. David Slama will respond to questions that have been posted by the delegates. With those words, over to you, David and Mr. Gilad Shainer.
Hello, everyone. I'm Gilad Shainer, and I'm happy to have you join me in the session about cloud-native supercomputing.
And I'll be here to answer questions for people.
Thank you.
Hello, everyone. I'm Gilad Shainer, and I'm happy to have you join me in the session about cloud-native supercomputing. So before we talk about cloud-native supercomputing, let's look on what's happening in the area of high-performance computing. We actually seeing that more and more high-performance computing applications are being created. More and more people, users, need to have access to high-performance computing infrastructures. AI and HPC are going everywhere. In the future, every company in the world will use AI, will use HPC. We'll see more applications, we'll see more users, and our supercomputing infrastructures will need to be more of a multi-tenant environments. Today, if we look on what kind of computing infrastructure we can use, On one side, we have the traditional supercomputing platforms. Great systems provide bare metal performance, but they lack the capabilities to support multi-tenancy. They lack the capabilities of security, of isolation. And the main reason is that by adding those services, those infrastructure services, we're gonna lose a lot of the supercomputing performance. On the other side, cloud infrastructures are great infrastructures that are built for multi-tenancy, for security and isolation. But since they're running that infrastructure service on the CPUs, they're actually losing performance and they cannot deliver bare metal performance. This is the reason for the creation of a new architecture, an architecture that is called cloud native supercomputing. It's an architecture that combines bare metal performance, actually accelerated bare metal performance on one side, with secured multi-tenancy on the other side. There are several technologies that enable that new architecture. Part of them are the creations of DPUs, data processing unit. The other part is adding more capabilities into the interconnect infrastructure for performance isolation and so forth. In this session, we will go into more details on the different components and what are the elements that they are enabled in order to build the cloud native supercomputing architecture. So first, looking on the different components of the networking fabric or the data center networking infrastructure, we have the main three components. The switch network, and from Nvidia perspective, we recently announced the Quantum 2 InfiniBand platform, which enable us to move to 400 gigabit per second speed and deliver greater in-network computing capabilities and so forth. So the switch fabric or the Quantum 2 InfiniBand switch fabric is the key element for multi-tenant in-network computing and for multi-tenant performance isolation. As on the NIC side, ConnectX-7, it's the latest InfiniBand device, 400 gigabit per second with PCI Express Gen 5 interface. And last and not least is the Bluefield 3 InfiniBand data processing unit or DPU. The DPU is the key element that enable us to bring more infrastructure services, such as security, such as multi-tenant isolation, without reducing from the total data center performance or the supercomputing performance. So before we go into the main components, let's look on the advantages of the Nvidia Quantum InfiniBand network. InfiniBand network provide actually two kinds of services. On one side, it's providing the most advanced networking services, such as highest throughput and lowest latency and high message rate. InfiniBand is the only network that is fully transport offload with hardware-based RDMA, minimizing the CPU overhead and enabling to move data directly from the network to the CPU memory, to the GPU memory, from the storage to the GPU memory, and so forth. InfiniBand also deliver enhanced adaptive routing and congestion control and quality of service, key elements for enabling performance isolation in a multi-tenant environment. On the other side, InfiniBand also provide in-network computing engines, in-network computing capabilities. Those are computing engines that sits inside of the network devices and deliver the capabilities to enhance or improve data algorithm performance and migrate algorithm from the host to run them on the network. The InfiniBand network includes engines that are set for very specific elements such as data reductions, tag matching and rendezvous offload, all-to-all operations, and many more. Beyond of those specific engines that are set for specific algorithms, InfiniBand also includes programmability programmable engines, such as multiple ARM cores and programmable data path, which exist inside of the Bluefield DPU. So if we're looking in more details on the DPU, on the Bluefield data processing unit, and looking on the architecture of this device, we can actually see that the DPU, it's a full data center on a chip. It includes the ConnectX network interface, meaning all of the NIC functionality is inside of the DPU. Beyond of the ConnectX, it also includes multiple ARM cores, different kind of acceleration engines around infrastructure management, security, encryption, storage management, and others. There is memory interface with memory on the card and a PCI Express switch device that enables to connect PCI Express devices directly to the DPU, such as flash or GPUs and so forth. So actually the DPU, it's a full data center on a chip. It's a full computer by itself. And by utilizing the DPU or using the DPU instead of the standard NIC, we're actually enabling a new computer inside of our computer, a new Linux machine inside of our Linux machine, for example. And this new computer can actually take responsibility for running the infrastructure workload, which means we can offload and accelerate the infrastructure workloads on the DPU, freeing the host CPUs for the applications, and in that case, enabling bare metal performance on one side, while for the first time, enabling multi-tenant, enabling security for our supercomputing platforms. The DPU can also be used to migrate and accelerate the communication frameworks, such as MPI, SHMEM-PGAS, or Nickel. And by migrating those communication frameworks into the DPU, we can achieve for the first time overlapping between compute and communication, which means we can get to a zero latency for the applications, for our high performance computing applications. So the cloud native supercomputing architectures looks as you can see here. In the traditional supercomputing architecture, we need to have the management, isolation, monitoring, as well as the storage management all run on the host. That's why we're minimizing those services in traditional supercomputing, because it reduces from the performance we can get. As well, we're also running most of the communication frameworks or the algorithms of the communication frameworks on the host. In the cloud native supercomputing architecture, we are offloading, isolating, and accelerating the infrastructure workload, the infrastructure services, the management services, the isolation services, the monitoring services, the storage services, running them on the DPU. We're utilizing SDK, software development kits, and runtimes of Docker and Magnum IO to expose the infrastructure services to the applications running on top. And with this new architecture, first we isolate between the infrastructure domain and the application domain, enabling much greater security, moving the supercomputing towards zero trust architectures, as well as enabling to bring those multi-tenant services without increasing overhead on the host side. So this is the key element. This is the key design of cloud native supercomputing architecture. So by migrating and offloading and accelerating the infrastructure workloads, we are isolating between the application domain and the infrastructure domain. And now the DPU can enable us to migrate the supercomputing infrastructure to a zero trust architecture. We are moving the storage management, as I mentioned, and exposing the storage services through VirtuaUFS. We're bringing a further security and actually isolating the users on the node itself, and keeping the rest of the infrastructure fully controlled by the DPU. That enables to bring service level agreements. And with InfiniBand infrastructure, we can isolate more than 30,000 concurrent users on a single subnet. Now, with the key ability of InfiniBand to move data directly to the host memory, locally or remotely, utilizing hardware-based RDMA operations, we can also migrate communication framework work to the DPU and have the DPU progress non-blocking operations, deal with active messages, manage smart MPI progression, and many other activities, many other user-defined algorithms that can actually run on the DPU closer to the data, and then provide the insights for the CPUs running inside of the server or the GPUs for their analysis of the data. We can see some of the results of migrating non-blocking MPI operations to the network. By doing that, by moving the work to the DPU, first, we can improve MPI non-blocking operations by around 2x. And you can see that using or demonstrating a non-blocking all-to-all operations, non-blocking all-gather operations, or non-blocking broadcast operations. In average, we're reducing the time by half for MPI operations by moving those or offloading and accelerating them on the DPU. And by moving MPI operations to the network, we can actually achieve full overlapping. Full overlapping between compute and communication for the first time. And as we're achieving 100% overlapping, we actually reducing latency. We're actually enabling zero latencies for applications running on the host. This is a great benefit because it enables actually to improve application performance and bring us to the next level of performance capabilities. One example on the application is what you can see here with the three-dimensional FFT. Originally, the three-dimensional FFT application was written based on a blocking all-to-all operations. Working with the software developer of the three-dimensional FFT application, we're able to change or modify FFT to move from blocking all-to-all operation to utilize non-blocking all-to-all operation. And by using non-blocking all-to-all operations, we could now leverage the DPU to run the non-blocking all-to-all operations by continuing progressing FFT work or calculations on a CPU. That enable us to improve FFT performance by 1.3x. Great performance benefit, demonstrating the key capabilities or the key advantages of overlapping or of utilizing the DPU to run non-blocking MPI operations. We will see more applications following up, moving from a blocking design to a non-blocking design, which will enable them to leverage from non-blocking operations, leverage from the DPU, leverage from the cloud-native supercomputing architecture to bring greater performance results with multi-tenant and security and isolation. So I mentioned earlier, in order to expose the services of the DPU in a very simple way to the applications running on top, which could be infrastructure applications or scientific computing applications and so forth, we have created a software development kit or runtime called Docker. Docker enable all of the services, the storage services, the networking services, security services, telemetry services, MPI services, even user-defined services to the applications running on top or running on a server. And by doing that, every element that is being written over Docker will be able to run on current generation of the DPUs, can run it probably faster on future generation of DPUs and so forth. So that enables folks with the capabilities to write the application once and then be able to leverage the DPUs in its future generations as well. Another aspect of multi-tenant environment is performance isolation. And performance isolation is key because as we're moving from a single job on a supercomputer to multiple users, multiple jobs on a cloud supercomputer, one job can impact another job performance. And this is a big issue for multi-tenant environments. You can see an example here where we took a molecular dynamic application called LAMPS. And first, and as you can see on the left side, we run LAMPS as a single job on a supercomputer. And we run LAMPS over and over and over again, many iterations. And every time we run the molecular dynamic code, we actually got the same performance. You can see the histogram here that demonstrates the results, number of iterations and the time. And you can see that in every iteration that we run, we actually got the same result as the molecular dynamic code is the only application running on the system. Now, if we take in the same application, our same application and running that on a multi-tenant environment, now the application running in presence of other jobs, could be storage jobs, could be massive all-to-all jobs, could be other scientific computing jobs and so forth. What we're seeing here is that one job can impact another job performance because they are competing on the same networking services. And now we don't see a very narrow histogram, we actually see a very spread histogram. Some cases we get good performance, some cases we get half of the performance, but there is no predictive performance here. Every time we can get different kind of result. By bringing a combination of a proactive and reactive congestion management into the network, congestion management that is based on telemetry data, time sensors, ability to plan traffic. The Nvidia InfiniBand network enables to bring performance isolation, full performance isolation into our cloud native supercomputing platform. You can see the results here on the left, comparing running the same molecular dynamic job, running the same LAMPS job, but comparing the performance of running that as a single job versus running that in an Nvidia cloud native infrastructure in the presence of other jobs or other users. And you can see that actually we're getting the same results. So the cloud native supercomputing utilizing also the proactive and reactive congestion control, an advanced congestion control mechanism on the InfiniBand network, enables also to bring performance isolation, full performance isolation into cloud native supercomputing architecture. You can see some recent results that we have run together with Microsoft on Azure, on HPC Azure. And here we tested different kind of workloads, the molecular dynamic with LAMPS or CFD or quantum mechanical with VASP. And actually we did the same exercise and you can see the results here. On the left is the histogram showing running just one single job over and over again on the cloud instance. As you can see, those are very narrow histograms, which means every time we got the same result. In the middle, you can see what are the performance results of these applications in the presence of other jobs in a multi-tenant environment. And here we can see a spread histogram where we don't have predictive performance, where we don't have performance isolation. Each time we can get different performance results for our applications. And then with the ability of congestion control of the Nvidia Quantum InfiniBand platform, we can see that we actually delivering the same results in a multi-tenant environment as this job is running as a single job. Full performance isolation, enabling predictive performance or enabling the same performance in the presence of multi-jobs or multi-tenants. So we're proud with the Quantum 2 InfiniBand platform, enabling multi-tenant in-network computing, multi-tenant performance isolation, enabling the cloud native supercomputing architecture. The 400 gigabit per second speed with higher switch radix, enables to accelerate data center performance while reducing power consumption and reducing space. We're looking forward to see a great adoption of the NVIDIA Quantum 2 InfiniBand platform and seeing more and more supercomputers, cloud infrastructure, AI systems utilizing this network to achieve great performance. With that, I want to thank you for listening, and we'll be very happy to answer any questions that you have. Thank you very much. With that, I want to thank you for listening, and we'll be very happy to answer any questions that you have. Thank you very much.
Thank you. Let's thank Mr. Gilad Shainer for an informative presentation about GPU accelerators on the cloud computing, which is slightly different from the traditional supercomputers like distributed memory systems, clusters, and shared memory systems, MPPs, and so on.
With that, I want to thank you for listening. We'll be very happy to answer any questions that you have. Thank you very much.
Okay, yeah, so now we're gonna go to the question. Let's thank Mr. Gilad Shainer for an informative presentation about GPU, which is slightly different from the traditional supercomputers. The voice is coming like distributed memory systems, clusters, and shared memory systems, MPPs, and so on.
With that, I want to thank you for listening. We'll be very happy to answer any questions that you have. Thank you very much.
Okay, can you please switch the now we're gonna go to the question. Can you please switch up the presentation? Shainer for an informative presentation about GPU. Thank you. Which is slightly different from the traditional supercomputer. The voice is coming like distributed memory systems, clusters, and shared memory systems, MPPs, and so on. Can you please switch on the presentation? Yes, I was saying that I would like to thank Mr. Gilad Shainer for a very effective presentation that he have presented it to us today. And then we have got 1 minute or 2 minutes for the question, and Mr. Slama is there to answer those questions. Chat box, I can't be able to see if there is any chat, any question. I don't see any question from the delegates. And then while maybe our technical advisor is still posting the questions, I've got 1 or 2 questions for you, David. And the first one, how do you envisage the future of GPU accelerator in the cloud computing space? And the second one is that does the GPU accelerators work very well with Intel and all other process capacities that we know?
Hi. So today we have several plugins that we are offering for integration between the GPU and the DPU and the other nodes in the network. And we are doing this in an efficient way, very efficient way, in order to offer new generation of supercomputing and the cloud native supercomputing based on isolation, offloading, and a security aspect that we are covering on top of the DPU for tenants and infrastructure of clouds. What was the other questions?
The other question that I asked, it was about how do you envisage the future of GPU accelerators in the cloud computing space?
Again, it's offering offloading capabilities on top of the DPU in order to do more stuff on the CPU side. And also we are offering on the DPU side also a security level that can protect the x86 for customers. So if we are talking about cloud native supercomputing, it's offer for customers full solution based on x86 with all the security aspect that we are providing for isolation and security and protection on top of the DPU. And also some of the services can run on top of the DPU in order to get more offloading capabilities and to make sure that the x86 is moving very fast without any interruption.
Thank you very much. Yeah, I see we still do not have any questions from the delegates. And thank you, Mr. David Slama, and you'll also pass our thanks to Mr. Gilad Shainer. Thank you very much. Yeah, now our next speaker is Dr. Duncan Roweth. Dr. Duncan Roweth is a senior distinguished technologist, HPC and AI CTO office at HPE. Duncan is a key contributor to the HPE Slingshot program, working on development of the second and third generation products. He joined HPE with the acquisition of Cray. At Cray, Duncan provided technical leadership on the NIC switch ICS. He was lead investigator in Cray's Exascale design project for the US Department of Energy. Before joining Cray, Duncan was a founder of the UK-based networking company Qualtrics. He has worked in HPC systems and networking for over 30 years. Thank you. Over to you, Dr. Roweth.
Thank you for that kind introduction, Samuel, and welcome to everybody. Welcome everybody to this technical session. I'm going to talk to you about high performance computing at HPE, and I'll tell you about some of the things that we're working on now and some interesting projects that are going on in the future. Okay, so as Samuel mentioned, I work in the CTO office, and my job at HPE really is to look at direction of our future high performance computing products and where we're going to invest and what areas we're going to concentrate on in the future. So the company has unrivaled experience in HPC and AI. And our business unit, we brought together teams of people from SGI, from Cray, and from HPE and HPE itself. So we have a huge performance team. We can rely on the HPE supply chain for delivery of these enormous systems that we work on. And our own research activities are complemented by those that go on within Hewlett-Packard Labs. So we're looking to build differentiated IP and systems capabilities. We're looking to focus on the key components of the system, the things that make our machines special. We work on high performance networking, on photonics. There's a lot of emphasis on memory-driven computing, so scale up large memory systems as well as scale out systems. And of course, we have our own high performance storage and data management division, and then the much wider storage work of the whole company. So we're investing heavily in the software for these systems. I came from Cray, obviously, and one of the key pieces of Cray IP is our programming environment. So at HPE, that's being made available to a much wider group of people so that it can run on individual servers and on clusters as well as on supercomputers. We're also investing heavily in the software infrastructure for these machines, whether they be supercomputers or whether they be cloud infrastructure, and on the sort of bringing those two themes together. One of the things we see a lot in HPC at the moment is what we call converged workloads. So that's combining simulation and AI, building them together into coupled workloads, adding in analytics capability. Then, of course, at HPE, we're working on delivery of these systems. So how we can provide flexible financial and delivery models for all customers and any size of systems, whether the machine is on-prem or in a colo, whether it's in a public cloud, and whether it's being financed through capital expenditure or as a service. There's a big drive to as a service within HPE as a whole at the moment. Okay, so clearly the background for this is delivery of the Exascale systems, and I worked for the last few years on the technology that's fed into the big US Exascale systems. But you'll see that there's a whole raft of other machines that we're working on that build on the same technology at lots of different sizes. So looking at the requirements, particularly on the software for these systems, clearly we need to be able to scale up to large system size. We need to build a productive environment. So that's an environment where we minimize the time to first execution of your program. And then once it's running, we make efficient use of the available resources. Some of you may be familiar with a parallel language called Chapel that was developed at Cray that was specifically targeting that first objective, minimizing time to first execution, making productive use of people's time. And that's a big theme in our programming environment generally. Clearly, we're trying to optimize performance of whole workloads as well as individual systems, and we're moving to this. We're moving to a position where we can provide everything as a service, so that supercomputing capabilities are available within cloud infrastructure, and that people can call on those resources, anywhere and anytime. So key piece of that software IP is the programming environment. As I mentioned, it was developed at Cray, and we're building in components that came from the SGI and HP heritage as well. So we're looking to provide a whole tool chain for managing individual applications and increasingly whole workloads. We're looking to do this in a way that isn't processor specific, so that we can support different types of CPU and GPU within the same infrastructure. Our customers' investment in software lasts much longer than any one system, and they need to be able to provide an efficient, easy to use programmable environment, but they also need that environment to last over long periods of time and provide portability, performance portability, including that from one system to the next. Okay, a quick discussion on HPE efforts in COVID. This is something that has had quite a priority within the company. Lots of my colleagues are working on these projects, supporting researchers in the academic community and in some of our commercial customers. And one of the things that it illustrates is a new type of workflow that we're seeing a lot of at the moment, where HPC simulation, in this case, molecular dynamics, is coupled together with other elements of the workflow. In this case, we're coupling an AI-based screening of molecular database to find good candidates to be used in imminent molecular dynamics simulation. So it's an example of a more sophisticated workflow that we see increasingly, and one that's had a lot of focus within the company as we all adjust to different ways of working. Another tool that we've been using in this environment is Cray Graph Engine. This is a graph analytics tool that was developed to run on, some of you may remember, Cray XMT systems, which were highly multi-threaded large memory machines. Well, Graph Engine is a software version of that system that runs on, these days, on supercomputers and on scale-out memory systems. And this team have been using it to build knowledge graphs that enable them to sift through tens of millions of publications that might be relevant to this. The number of papers being produced per day in the pharma industry is enormous. Finding a way of gathering information and extracting knowledge that's relevant to a particular problem is a real challenge. So we've been working with a team on use of Cray Graph Engine for this problem. So there's some further information that we put together for anyone who's interested in what HP is doing in this field. Okay, so I'm going to talk to you next few minutes about our HPC and AI portfolio and the capabilities that we've been putting together, the technologies that we've been using, and how they get deployed. So clearly the key pieces of the infrastructure for these exascale systems is the interconnect itself, the power and cooling infrastructure that enables us to run these big systems, a software stack that can operate over tens of thousands of nodes, the processors themselves, I'll come on to those in a minute, and then high performance storage systems that that allow us to build these couple workflows and allow the long running simulations, for example, to save their state as they run. Okay, so some examples of the components that make up these HPE Cray EX systems. So this is our workhorse scalar compute blade. It's built from AMD now Milan CPUs. You'll see it track future AMD CPUs. And then we give each of the nodes in this system, this blade here has 4 dual socket nodes, and we give each of those nodes either 200 or more normally 400 gigabits a second of network bandwidth. You'll see a number of systems that are made up of this blade. The next design uses an Nvidia accelerator. So this is these are the systems that we've started shipping to. NERSC, for example, has one of these. So we use the same overall form factor, the same network infrastructure, the same powering, cooling infrastructure, but the nodes are different. And this time the nodes are made up from a Rome CPU and four GPUs. And then in these machines, they have either 400 or 800 gigabits a second of network infrastructure, of network bandwidth. So we've put multiple network interfaces into each of these nodes to scale up the injection bandwidth with the computational capacity of the nodes. So in these pictures, you can see mostly the cooling infrastructure, but you can see the NIC mezzanine cards at the front, and there's an interesting technology for cooling the NICs using the CPU's cooling infrastructure. You can see the GPUs towards the back of these cards. So the NERSC machine is built up of these Nvidia GPUs combined with AMD CPUs. Then if we look at the machine that we've started delivering at Oak Ridge, we're also supplying this style of machine to Pawsey and to the Lumi supercomputer site in Europe. This is made up of the new AMD GPUs combined with an AMD CPU and 4 of our NICs. So each of the nodes in the system has 800 gigabits a second, so roughly 100 gigabytes a second of injection bandwidth. That was one of the key metrics of the exascale systems early on. They were looking to get 100 megabytes a second in and out of each of the nodes. That's achieved by using more of the network infrastructure that can go into the EX cabinets. The EX systems can have fairly thin network, or they can build up, giving each node 1 or 2 or 4, potentially even more network interfaces. So that scales nicely with these multi-CPU or multi-GPU designs. It means that you can give each of the CPUs or each of the GPUs direct access to the network. So that network is built up of our Slingshot technology, which, as Sam mentioned, I've been working on for the last few years. So this is a high-performance Ethernet, and we use Ethernet physicals. We can interoperate with anybody else's Ethernet switches, and then we start to build support for HPC protocols in there as well. So it's open and standards compliant at the edge, and then it has advantages of our adaptive routing and our congestion management within the system. So we've been shipping this for a while now, and the network is based on a 64 by 200 gigabit switch, and we've recently announced the NICs that connect up to the system. So there are 4 of those NICs, for example, in each of the GPU nodes. So this network provides us standards compliance, interoperability, but it also provides us with efficient congestion management and low and uniform latency, so that when one of these machines is operating in a mixed environment with lots of different applications running at the same time, then heavy load or congestion coming from some of those applications can't impact others, which is an increasingly important property. So this is the network technology we're using in our high-end machines, and you'll see thousands of these switches in those big systems. So that we then combine that with our supercomputing software stacks, and we support a couple of different types of stack for different sorts of users. There's one that takes a very traditional approach. It's based on HPCM, so the HPE SGI heritage. It allows us to take a set of components, build images from with the right blend of components for an individual customer, to deploy those very quickly and to manage their execution on these very large systems. The other stack that we're building is a microservices-enabled cloud stack for HPC. So this is a project that had been going on within Cray for some time, and it represents a direction in which we see some of our HPC customers taking in the future, and it's a direction that the company is taking for wider enterprise and commercial use of HPC. So if a supercomputer system is like a big experiment, targeted on one application or one workflow, or a small number of very high-end users, they might trend towards the first stack. If the customers are looking at how they evolve their workloads into a multi-tenant environment, how they embed supercomputing within cloud infrastructure, then they might look at the other stack. Obviously, they have lots of common elements: the Slingshot fabric, the operating system, the Cray programming environment. But they represent different ways of managing these systems. Okay, so this technology is allowing us to deliver machines over the next few years. You'll see big systems being deployed at Argonne and at Livermore, as well as the one that we're putting in at Oak Ridge. You'll see the Lumi system, that machine's already in place at the moment and is being expanded. The same for the system at NERSC, and you'll see other machines at the one at Los Alamos, for example. They're all built on these same components. And this is the list of publicly announced contracts to date. There are lots more of these systems that we'll be announcing in the future. So I'll wrap up with a direction that we're seeing these machines going in the future. We're seeing what we like to describe as a Cambrian explosion in terms of the different types of processing resource that are being developed in response to slowing down of the performance of the mainstream processors. So It's really slowing down, and the gains in, that curve in gain performance is flattening off. And people are looking to achieve performance through specialization. And there's a huge number of startups all over the world who are building custom processing ASICs, each attacking different specialist problems, lots of them problems in AI or accelerating AI operations, but others focusing on molecular dynamics or other areas of high performance computing, simulation problems. So we see this huge explosion in different types of processing. And of course, this is both a problem and an opportunity, in that you want to be able to adapt existing codes to run on these systems. You want to be able to use as much of the existing infrastructure as you can and rewrite core elements of them to achieve the best from a particular a specialist processor operating in a particular way. So we're looking at how we can build a system architecture that adapts to this this wide range of processing capabilities, and build system software that can support them, so that you'd be able to take the environments that we're building for CPU and GPU based systems and run parts of the workload that need this specialized processing on particular types of CPUs that are well suited to that one task. So you might see some cloud infrastructure that has pools of this resource and pools of conventional CPU and GPU resource, and a workflow that spans all of them. So this is an example of a system we built this way for Pittsburgh Supercomputer Center, using the Cerebus wafer scale integrated accelerator. This is quite an incredible thing that has huge numbers of individual accelerators on a wafer and couples them all together within the wafer, and then couples them to the outside using a set of Ethernet interfaces, which in this case we've hooked into a SuperDome Flex. So you can see that you can envisage this system as a high-end workstation, really, which is the SuperDome, and then it has all of this accelerated compute coupled closely into the that general purpose processing resource. And then clearly the team who are working on this are looking at how they build applications that are hybrid between the two. So while we see the growth of these big CPU and CPU-GPU based systems, we also see lots of these specialist systems that are developing, and we're looking at how we build our tools and customize our workflows to use them. And then lastly, of course, HP is working on delivery and how we provide this resource to you. And so GreenLake is our vehicle for cloud-style deployment. And that might be on people's premises, it might be in a shared data center, it might be in a colo, it might be in a public cloud. We're looking to build an environment where these resources are available self-service, where you commit to some amount of CPU use, some reserve of use, and then above that you pay for what you use. People get to scale up or scale down their resources, and they get to deploy the software stack that they want to see in this machine. So GreenLake is the project as a whole within HPE for delivering everything as a service. And our team works on building supercomputing style infrastructure that will integrate into that environment. Okay, so I'd like to thank you all for listening, and then return control to Samuel, and we'll see if we have any questions lined up.
Thank you, Dr. Roweth, for sharing useful information about different technologies that are on HPE. We really appreciate your time and effort to join us in this conference. Looking in the chat box, I cannot be able to see any questions. There's no questions, basically, that have been posted by the delegates, but probably they are still coming. In the meantime, maybe let me ask a question, and hopefully it is not a controversial one.
Controversial questions are fine.
Yes. Oh, yes. Because it's going to be a question of the products. So how does the parallel programs perform in the HPE Slingshot network compared to the Mellanox, InfiniBand, and Ethernet network?
Okay, so I mean, clearly they perform much better on a Slingshot network. You wouldn't expect me to say anything else. So why is that? Firstly, the team that developed Slingshot had worked on many previous generations of machine, and we had looked at the issues that arise on those systems when there's a mixed workload on a machine. It's all well and good to get good performance running with one application running on a machine. You know, you need good bandwidth and low latency. You need progression of MPI operations so that you get good overlap of comms and compute. And we have all of those things. But when you're building a hybrid workflow, or you have a machine that's running lots of jobs at the same time, what we want to be able to do is to control allocation of the resources in that network, so that applications which need low latency continue to get low latency even when there's a high workload on the network as a whole. And the applications that need a certain amount of bandwidth in order to run well, that they get that even if there's somebody else using the system at the same time. Also, if you've invested in an expensive storage system that can provide high bandwidth data movement to and from your application, you want to make sure that you get the peak performance of that network, of that storage system, and delivered through your network. So you need strong quality of service metrics in the whole system. So so we've been working hard on this area. We've been working hard on offloaded MPI performance, and on the scalability of the applications so that they run really well on these big machines. You'll see we're working on new generations of Slingshot that operate at higher speed and have more sophisticated offloads. So we're going to maintain a highly differentiated product. Some HPE customers use InfiniBand. We use it in our storage systems. Some people use it in their clusters. And of course, it'll continue to be available in HPE clusters.
Thank you, Dr. Roweth. I've got a question for you from one of the delegates. The question is, I'll read. Thank you for the great talk, Duncan. Very interesting to see all the new developments coming down the line in terms of heterogeneity and custom ASICs. Is the most of the action happening in GPU type many core architecture, or is it variety?
It depends on it varies between the companies. So the big companies, Intel, AMD, Nvidia, they're working heavily on GPU infrastructure. They have GPU lines. You know, Intel will be introducing these soon. We see those in the Aurora Exascale system. It's all the small companies who tend to, who are looking at niches and at building special purpose processing for a particular niche. So it's quite a split between the two. And then, of course, some of the smaller companies get acquired by the bigger companies, and their products start to feed into more mainstream processing. So it's an age of the small companies at the moment, but these things go in cycles.
Thank you, Dr. Roweth. It seems like we don't have further questions. Yes, there's no more questions.
Well, thank you, Samuel, and thank you to people who've joined this session today. And you know, I hope you enjoy the rest of the conference and it's productive for you. Bye-bye.
We appreciate that. Okay, thank you very much. This is the end of the session. And then the next session, I think, is going to start in about 15 minutes. There is a break from now until 12:15. With that, thank you very much.
Bye-bye.
Bye.